I think everybody was younger. I wonder if I go there for the camera, can you see me? But I'm in front of that screen now. I'm seeing myself.
So it is there. Someone just logged into it.
Oh, cool. It's called Live Events. It's a live event. FHL REU Student Presentations. Can you see me? Yeah, that's okay. Perfect. Okay.
They just call it sitting home. And then my friend Jeff, local meditator. Yeah. That's daddy. And it's there is a way back. There are things that so they're kind of worried. Yeah, I told some people that you know that's So they have a big farm. And her Ellie's birthday was 2 days ago.
You're good. Very good.
So, kind of small. I don't know what this is, but I like it. I just had one of my friends here from Israel. It's nice to see.
Anyway,
Well, very little
anyway, this is
I didn't think that I could have tagged or to they might have.
All right, I think we're ready to begin the second session of the Police REU Symposium. Thanks all for being here, and we have a lot more great talks. We had a great afternoon session, a great evening session here, and so without further ado, since we have many talks, I want to introduce our first speaker of this session, Lisa Truong of Wellesley College, and her mentor is Petra Beecham.
Okay. Hello, can everyone hear me? Awesome! Okay. So, for my presentation, I looked at the northern conditions, the environmental wave forces, and the effect of water levels on the distribution. It's kind of a lengthy title, and a few of my peers actually had some more original ones, so I thought of something that's a little funny. So this is my second title. Stuck at fish, how to speak Klingon and use the dark side of wave forces. So, the area between high tide and low tide. And there are two sources of stress, one of them being the vertical. And that's a result of the alternating tides. So with increased exposure comes increased stress. A second is the horizontal, and that's a result of the differences in wave action between exposed and sheltered areas. And of course, when we talk about wave velocities, there's a lot of physics involved, but two of the more important terms to remember are lift and drag. So lift is a vertical force, and drag is a horizontal force. So in the intertidal zone, we find northern clingfish. So as you see the top photo, this is the fish sticking itself onto the rock. You're probably thinking, how does this work? Well, the clingfish has modified pelvic fins that act as a suction disc, and so it uses adhesion to stick itself onto rocks. But then you're probably wondering, sometimes rocks are crooked, they're not straight. How does the clingfish prevent itself from sliding, or like sliding off the rock? And so forces at play there are friction, which act parallel to the surface. And so friction are represented by these two roots. And if you look down here, these are SEMs of the microvilli on the suction disc. Pretty cool stuff. As you can see in this photo, this is a very small fish lifting a very large rock. And fun fact, this fish is dead. Well, my mentor in Anna Summers actually made a quick video, which I'll show you right now. And it's pretty cool. Whoa! Awesome. So that leads me to my two questions. What are the wave forces affecting clingfish? And how do water levels affect their distribution? So I set out to answer these questions. And so the first thing we had to do was select our site. And so we went to 3 different beaches on San Juan Island. And we ended up picking Ribbon Tart as our main site. And that's because we found the most clingfish there, 23 on one day. So I like to call this a picture of our office. So if you kind of look up here, that's my lab partner. And so every day that we would go to Ribbon Tart, we'd have to set up transect. And this is the before photo, but if you look here, this is basically what it looks like afterwards. And it's kind of complicated, this photo, so we can break it down together. What happened is we ran some fishing line, or rope rather, across here. We numbered them from 1 to 12. Then we numbered them, or lettered them, from -C all the way to S, from the seashore up to like the land. And we created about 250 transects, and they each measured 1 meter by 1 meter. But for ease of visibility for this presentation, I've kind of grouped them together into 2 meter by 2 meter squares. So we thought, now that we have these transects, it would be pretty cool if we could make a map. And unfortunately, we didn't have a helicopter, and Google Maps wasn't cutting it, so we did the next best thing. We took photos of each of the transects, and here are some examples. We then transposed them onto vellum, which means we drew them out by hand. And this is our final product. So as I mentioned earlier, those are the axes. And hopefully you can see it, but these globular things all over this map are the different rocks. And a fun thing to know is that we did not draw rocks on this map that were smaller than 10 centimeters in circumference, but also in our transect area, there were no tide pools. Okay, so how do we measure the maximum wave velocity? Well, we built dynamometers. And I actually have some examples here. I'll pass them out. And so the way that it works is pretty simple. You have a spring that is kind of housed in this PVC tube right here. And the spring is attached via a fishing line to a golf ball. And in between the golf ball and the spring is a rubber indicator. So as the waves act upon the golf ball, they exert a drag force, and that pulls the golf ball, and thus extending the spring. And the maximum extension of the spring is recorded by the rubber indicator. And from that value, we can calculate the maximum wave velocity. Pretty cool. So at Ribbon Tart, we put out 15 dynamometers. We put 9 in the transect area, marked by that blue circle. And the data we collected looked like this. And so as you can see, not all of the devices were activated, and that's because the minimum threshold of 1.1 meters per second wasn't reached. And that's totally fine. We also put 2 more devices to the left, marked in red. So as you can see, the maximum velocities never went over 2. We also put 2 more in front of the transects marked in green. And finally, we put 2 more on the far right in yellow. stepping back and looking at the big picture, you can see that the maximum velocities at Reuben Tart range from about 1.41 meters per second all the way up to 3.41 meters per second. And so we thought, is this calm? Is this like turbulent? So we thought, well, how can we figure that out? We can put up more dynamometers at other parts of the San Juan Island. And we did just that. And fun fact, we actually went up this morning to collect the data, so it's hot stuff, like hot data. So if you look over here, you can see that overall the San Juan Islands are, I guess, pretty calm waters. The highest measurement that we got was at Cow Point today, but it was about 3.1, which again does not exceed that 3.5 meters per second threshold we saw earlier. So looking at the other data we collected, we also looked at kingfish dispersion. And this kind of looks weird, but I can explain it. So each of these colored dots represent one kingfish. So for example, each of the white dots represent one of the 13 kingfish that we found on June 30th. And looking at this figure, you can kind of notice most of the fish were found in this area up here, like none were found down here. So we thought, why does that happen? So maybe it has to do with water height. So we set out to calculate that. So at our transect beach on Reuben Tart, Christina would stand at the top of the shore over here, and then we'd run a fishing line all the way down to the water to a transect. And then Petra would measure the angle in between. Using some simple trigonometry, the law of cosine, we calculated the height, which is this, A. And using that data, we made this really pretty picture. So as you can see, this is our water heights profile. All the blackness represents the height required in meters for water to reach the MLLW, which stands for mean lower low water. And as you can see, the negative transects require negative values. The positive transects require negative transects require negative values, and positive transects require positive values. That makes sense. So basically that means that our site was on a slope, and that the negative transects were submerged underwater a little longer than the ones up here. So let's look back at the kingfish dispersion. I picked these 3 specific days because these are the days that we found the most kingfish. So on June 30th, they were over here. July 11th, up here, and finally July 12th, over there. So we thought, maybe this has to do with percent time underwater. And the calculations for that are pretty fun and easy to do, so we'll do it together right now. So let's pretend we want to find the percent time underwater for transect C. And let's pretend transect C is about 4 feet high. So you want to find the points on this graph that are 4 feet. And fun fact, this graph is actually a graph of the water levels taken from the NOAA website. But anyways, those 2 points are marked by these smiley faces. And the area in between the smiley faces is the time that transect C would have spent underwater. So next, you want to find those 2 times, which happen to be 12:30 of August 7th and 5 a.m. of August 8th. And next, the hours in between those 2 points are about 16.5, and you want to divide that by 24 hours, which is 1 day. And thus, you see it's about 70. So that means transect C spends about 70% of the day underwater. Pretty cool. Okay, so we know that the tides, they change every day, and so percent time underwater had to be calculated for each fish and each transect in each day. Kind of a lot of work, but that's okay, I've already done it for you. If you look over here, this is the data for June 30th. So fish were found exclusively in the areas between 83 to 86% time underwater. Then, on July 11th, they were found in the range of 82 to 95. And on July 12th, they were found between 85 and 97. Kind of see a trend going on. So, taking a step back and looking at the big picture, you see that kingfish are found in areas that spend at least 80% of the time underwater. Fascinating. And this is actually just like another graphic showing the specific kingfish. Pretty cool. So, in summary, we can see that at Reuben Tart, the maximum wave velocities never really exceed 3.5 meters per second. And so we kind of concluded that maybe the waters around the San Juan Island are relatively calm. And that's pretty cool. So we kind of think that they represent not necessarily the upper threshold, rather the lower threshold for forces that the kingfish can endure, which is pretty fun. Then also I would definitely say that this experiment was a success because future people, if they want to look at other wave velocities, can actually use our method. For example, if you're measuring similar wave forces, you're going to want to have sensitive springs. Because, fun fact, in the beginning, when we had made those devices, we were like, oh, they're super cool, let's send them out. And we actually couldn't get data because, oh no, the springs weren't sensitive enough. So science is kind of like trial and error, and that's what we did. That's pretty cool. But then another thing that we found was that kingfish, their spurgeon is correlated to tidal activity. So kingfish, as you can see, kind of spend most of their time in transects. Kingfish are found in transects that spend most of the time underwater. And so remember we looked at water height, and we also looked at the percent time underwater. And of the two values, we definitely say that percent time underwater is maybe a little more important as a framework for determining where kingfish are moving. So looking towards the future, it'd be pretty cool to find out which wave forces actually act on the kingfish, because our study really kind of looked at the available wave forces. And another thing is that we really studied Ruby Tart, but then also the San Juan Island. But we do know that kingfish are found in Europe, but also Australia. So it'd be really cool to compare the wave forces in those different areas. And then, acknowledgement, I would definitely like to thank Petra, because she's an awesome, awesome mentor. Christina Lincoln, being a great, great lab partner. And then Carrington for our help in building the maximum wave velocity measurement devices. The FLIMS program, the NSF REU, Summers Lab, Friday Harbor Labs. My two mentors at Camilla College, Jocelyn Dill, Louis Starla, and all the other REU students. Thank you.
We have time for questions.
Okay. How far are they actually traveling when they move with the tides? And the second thing is, you know, where they are when they're in the transit, how are they moving? Are they taking sleep with the water? Are they sleep
Okay, cool. So actually, my partner is going to be presenting after me, and she kind of studied the habitats. That's really fun. So trying to answer your second question, how do they move between the transects? Well, we don't really know, because what we did was we went out there, we flip rocks and find them, but we didn't actually see them like moving from rock to rock. But it'd be really cool to look at that as a future study. And can you repeat your first question? I totally forgot. So sorry.
How far?
How far? So for our study, our transects were about 1 meter by 1 meter. So I know like a couple of the fish. Oh, actually, that's luck. We don't really know how far they went because we didn't actually look at fidelity. So we would like measure the fish and like get our data for that, but we didn't track them. So we didn't like put them back and know where they ended up next. So if you look at that map again, each of those dots represent all the fish that we found. But I think I should have said earlier is that those fish may have been like 60 different fish or like the 12 same fish over and over because we just looked at them on different days. Did that answer your question? Oh, yeah.
We have time for one more question.
So as time went on, your fish sort of moved closer to the water. Did you get any sense at all as to what happened?
So we didn't do any data collection for temperature, but reading the literature, a lot of people have actually linked temperature to like the tides and the percent time underwater. So I definitely think they're correlated, but we didn't actually study it here. That'd be fun, you know, but.
Thanks a lot. All right, next up is Lisa's writing partner, Christina Lincoln from the University of Hawaii at Manila, and her mentor is also Petra.
Hi, so as I said, I'm Christina, and today I'm going to be talking about the ecology and habitat structure of the northern kingfish. So the northern kingfish is found in the intertidal region, ranging from Mexico to Alaska. And if you guys don't already know, the intertidal region is a really harsh environment for animals to live in. They have to deal with the ebb and flow of the changing tides. They have to deal with the risk of desiccation, which means drying out, and that's because of the extended immersion that they have to deal with. They also have to deal with crashing waves in their environment, and not only those things, but they have to deal with predators, both aquatic and terrestrial. But luckily for the kingfish, they are morphologically well adapted to handle these these tasks. So one thing is that they can breathe in both land and water. They can camouflage themselves against the rocks so that they can hide from predators. And probably the most well-known morphological adaptation is their modified pelvic fins, which act as super suction discs, and you can actually cling the fish onto your forehead and they'll stick pretty well. So Petra found that tenacity is high on both fouled and unfouled surfaces, and furthermore, Wainwright has found that kingfish are able to cling on to not only smooth surfaces, which is what would be kind of expected, but rough surfaces as well. So it's really impressive for such a small fish. And so these are all good morphological adaptations that are pretty commonly studied. But what's less known is the behavioral and ecological adaptations that kingfish have come up with. So one of the few studies that looks at this comes from Pires and Givron, and they looked at a different Bobia saucidae species, and they measured parameters in their habitat, such as attributes of the rock, so rock size, rock color, and Aufwuchs cover. And today when I use Aufwuchs, it's a term in German meaning periphyton cover on a rock, so it can be algae and barnacles and any other thing that's living on a rock. So these parameters have not yet been looked at for the northern kingfish. So with that in mind, I asked these questions. What is the range of rock sizes that kingfish prefer? What is the range of Aufwuchs cover and biofilm that we find kingfish in? And what kind of substrates are understood in the field where we find kingfish? So to answer these questions, we had to choose a study site on San Juan Island that was not commonly trafficked by visitors and tourists, and one where we found a lot of kingfish, and one that was relatively exposed from a low to mid-tide. And as Lisa said, we tried looking at Paddle Point and Dead Man's Cove until we finally decided that Rubentart would be our summer vacation spot / office. So if you guys can recall from Lisa's presentation, we staged transect lines running from the water line to the beach, going by letters, and then perpendicular to that line, we had 12 meters, numbered 1 through 12. Moving on, for data collection, we went out 10 times this summer between June 30th and July 24th, and collected a total of 63 kingfish. And we only went out during low tides that were lower than 0 meters. And so we flipped rocks systematically. It wasn't random. We actually went transect by transect, flipping rocks, looking for kingfish. Once a kingfish was found, we put it in one of these little buckets next to a lure. I was aware that they stayed that straight for us, but once we had this image, we took it into ImageJ and got their exact length. And besides the fish length, we looked at parameters related to the rock. So we looked at the rock size, we looked at length, width, height, and circumference, and then we measured the Aufwuchs cover just by giving an eyeball estimate. And then besides that, we looked under the rock and looked at what type of substrate that was under the rock. So it could have either been sand, gravel, pebbles, or other smaller rocks. And we also measured the biofilm just simply by feeling the rock and noting whether or not it was slippery. Essentially, no stone went unturned. We worked really hard. No stone went unturned. Except for maybe this one. It was a little bit too big for me. Okay, so what did we find? This graph is a bar plot showing the rocks that were available to the kingfish, seen here with this darker gray bar, versus the rocks that were actually selected by the kingfish, seen with this lighter gray. And you can see with this that kingfish selected rocks that were between 15 and about 55 centimeters in width. But what was available to them was, and it ranged between small pebbles to giant boulders. So you can tell that there's a clear difference here, but we wanted to run a test to make sure that it's actually significantly different. And a G-test did reveal that it was very highly significantly different. So this tells us that shelter selection for the northern kingfish is absolutely not random. So they're for sure picking a site or a range of rock sizes that is suitable for them. We found that there's no relationship between transect size or fish size and area of the transect, and this is from Lisa's. If you remember, these little gray things are rocks. Fish between 4 and 6 were noted with a small violet dot, and in case you can't see them in the back, here are some of them. And then yellow, the yellow dot represents fish between 6 and 9 centimeters, so there are some down here. Sorry if you can't see them very well. And then the giant red dots are representing the larger kingfish that were between 9 and 12 centimeters. Even though we didn't find any correlation between fish size and transect area, we thought this would be worth looking into because other studies had shown that there was a correlation. In another kingfish species, they showed that larger fish were closer to the water, and so they were in more moist areas, whereas smaller kingfish were up farther away from the water. And this is probably because their larger body has more surface area that is exposed to the air, so they're running the risk of desiccation, so they need more water. We initially hypothesized that rock size selection would be in correlation with fish length, but clearly you can see that there's no correlation here. The reason for this lack of correlation might be that even though small fish aren't selecting small rocks, it's likely because, so there's this line right here where there's a certain minimum threshold that kingfish need a certain rock size before they'll go under it, whether they're big or small. And even if it's a small fish, they're going to go under a rock that's a little bit bigger because in moving waters during high tide, that rock might be more susceptible to movement. So no fish is going to be want to be under a rock that's moving. One thing that we were not initially looking for, but that we found was that there's a bimodal distribution in fish size. So you can see here that there's fish between 4 and 6 centimeters in length, and then fish between 7 and 12 centimeters. But there's this obvious gap between 6 and 7. So why is that? We looked at a paper by Huston and DeAngelis that explains mechanisms in why there might be bimodal distributions in fish. And the most likely explanation for our study is that there's a gap in ages, suggesting that there might have been a decrease in reproductivity during one particular mating season. Kingfish were most commonly seen under a gravel substrate, and this trend is actually something that was seen in the Californian kingfish species as well. And they hypothesized that gravel is a good substrate for kingfish to burrow in when they're disturbed. But for our kingfish species, we think that gravel might provide a good balance between dampness to prevent desiccation and also aeration to allow the kingfish to breathe well on land. It should also be noted that kingfish were almost never found in sandy bottoms because it's evident when you flip a rock that has a sandy bottom, there's a really tight suction and there's not even room that a kingfish could really be under there, let alone air for them to breathe. So moving on from the underside of the rock to the surface of the rock, we looked at outflukes cover. And this graph shows the area of outflukes covered per stone versus the amount of times that kingfish were selecting that amount of cover. And you can see there's no real range of outflukes that the kingfish were found under. It seemed pretty, they range the whole spectrum from bare to 100% cover. But we also wanted to look into this because a different study had shown that the other Bovius saucidae species preferred bare to little outflukes covered rocks. So we thought we'd try it. But for the northern kingfish, outflukes doesn't seem to matter much. And finally, we measured whether or not biofilm is present on the underside of the rock, and this was to get an idea of the habitat parameters that the kingfish has to deal with. So for this plot, we said that fouling, if we felt that the rock was slippery, we said that there's biofilm present. If it was not slippery, we just said biofilm not present. So it's a simple plot, but you can see the huge difference where kingfish are found under rocks that have biofilm. And this tells us that biofilm is everywhere in the environment. And this is a really nice result to see in the field because in the lab, Petra showed that for the northern kingfish, biofilm is almost a trivial obstacle because they were able to cling on to surfaces whether or not they were slippery. And because they're able to handle these slippery surfaces, they might be more prone to be under slippery rocks, just because their prey item, which is the limpet, often grazes on rocks that are covered in biofilm, so they might be under areas where their prey is found as well. So to summarize what we learned about clingfish, here are some of the main points from today. Clingfish are very highly selective for the range of rock sizes that they prefer. Although there's no correlation between rock size and fish size, we did see a really cool unexpected bimodal distribution in fish size, and that would be really cool to look into and see why that is. We found that gravel was the most common substrate found under rocks where clingfish were found. And then finally we found that biofilm is pretty much everywhere. The rocks are all really slippery, and that's evident from just walking on the beach. You can tell that you're slipping all over the place. So clingfish have to deal with that, and this tells us that they're pretty well adapted to this habitat, and they just have to deal with it because there aren't any other options. And finally, I would like to point out some of the further work that still needs to be done. We want to quantify the range of roughness on the rocks that clingfish have to deal with. So what we've done already is taken casts, as seen in this picture, of the rocks, and we can actually take these casts back into the lab and quantify the roughness to get the full spectrum of the range of roughness that we're seeing them found under. And also, it would be interesting and informative to kind of see what fish are doing during high tide and at night, because it's kind of a time when clingfish are never seen, so I don't think anybody really knows what they're doing. So we would like to find that out. That would be really cool. And so with that, I'd like to thank the people and the programs that helped me get my summer research experience.
And we have time for questions.
Could you talk a little bit about where the clingfish is when it's under a rock? I mean, is it?
Yeah, so just right on a day when you flip the rock, there's kind of like a little pocket. It's not like it's flattened under the rock. There's a little bit of space. So that's probably why gravel and pebbles are where they're found, because there's a little pocket under the rock for them.
So are they hanging onto the rock that you pulled up, or are they on the ground?
Usually, I think they might be, when we pick them up, they fall off the rock, or there might be on, like, right side up, so it just depends.
Some fish you can tell their age by the illness. Did you try looking at the ages of any of those that you can find?
Yeah, not much is known about their anatomy, so we wouldn't even be able to sex the fish if we wanted to, so we also don't know how to discover their age either.
I believe that they can find on the sides.
Limpets are pretty much all over the rocks, yeah, so they don't really have a preference for bottom or top, just based on personal observation.
You'll find in the same rock.
Yep.
One more question.
So as the tides are going up, the fish must be able to feel the drag of the tide going up. Why do they stay up there? Why don't you just surf out? What's the benefit for hanging out under a rock when there's no water?
It might be that it's too late for them to leave. They kind of require water to swim. They can't really flop, it seems like. So I think that they would need to choose a spot while the tide is still high, and once they select that spot and the tide goes down, they're kind of stuck there until the tide comes back up.
All right, thanks a lot. All right, our next talk is by J.J. Lomax of the University of South Florida. His mentors are Stephanie Crofts and Adam Summers.
I want to start off by saying thanks now for you guys. Like, 8 o'clock, you guys get a place to put you here for science, so really give you science.
Yes, right here.
All right, so my study was entitled The Importance of Being Organized, a study on tooth ring's effect on derivation. So over the summer, I've been trying to figure out if there is a correlation between the efficiency of derivation teeth and the arrangement that you see these teeth in. So we can learn a lot about teeth, and from just understanding what type of tooth morphology you have, you can learn a lot about the organism as a whole. So from these teeth at the top here, you're going to see that this organism is going to be eating some sort of animal that needs to puncture into that it can get a good hold on, because it's going to be slippery, and if it lets it go, it has nothing to eat. So that'll be something that's usually eating a scaled fish that it can get straight into, hold on to it, and the fish is going nowhere. And these teeth over here, they're more knife-like, kind of cutting or serrating teeth that are going to get at an organism and from there slice it so that it's not going anywhere because it's probably going to be too strong for these puncturing teeth, but once it gets a nice good cut going down it, the organism's kind of just toast. So for these last set of teeth over here, these are more for smashing. And if you look at these two over here, you think of blades, you think of spears, you're like, oh, cool, weapons, they're going to be awesome for capturing prey. But what about these teeth here? There's not too much that you think goes into neurophagy, which again is, I'm sorry, this is the first time I'm talking about it, going to be the crushing of an animal by an organism. So anything that's going to eat a shelled organism is going to be a neurophagous predator. So why study neurophagy? Well, over the course of these different shell-crushing teeth, you think that there'd be some kind of uniform model that would be the best at smashing shells, but that's not the case. We see that in all of these organisms, which are all shell eaters, you're going to have this linear arrangement, you're going to have this kind of staggered arrangement, and you're going to have this kind of quad arrangement and this modified quad here. For my study, I decided to go ahead and try and model these arrangements to see how well they all would work at fracturing a prey item. So my models, again, taken from Inspiration Nature. So I have this linear arrangement, staggered arrangement again, quad arrangement, and then this modified quad. To make my models, we started out with a program called 1-2-3 Design, which is a computer program where you just tell the computer what you want, and it just throws it up there. So I needed to make a tooth that was similar in the arrangement to the organisms that we saw earlier, but also had that same malariform shape that you saw in your neurophagous animal in the bottom left of that triangle. So you kind of want that same robust, round type shape that's going on, and you want it to go ahead and fall into that same shape that you saw with the organism. So I made sure that the radius of curvature for each of these was along the line of a spectrum from negatively concave to positively convex, and I made sure that the circumference of each circle is the same so that we get this uniform tooth shape that's just going to be put in different arrangements. From modeling, we went into a program called SprutCam, which is going to be controlling a 4-axis mill. Now, 4-axis mill is really cool. I'm going to call it a toy, but it's not a toy. It's very, be careful around 4-axis mills and any kind of shop equipment. Very careful. But I still think they're toys that are awesome, and before this, I've had no shop experience. I made like one share with my dad. That was all I've ever done in the shop. But from these, this machine here pretty much does everything I tell it to do in that SprutCam program, and it drills out exactly what I want it to. The final product looks something like this. So these are my tooth models, and they're going to be made from aluminum metal, and there's 20 different models. I used 20 different models because the study before this had found that concave teeth and convex teeth both require different loads to fracture prey. For your concave teeth, there's a trend that they're going to require more force to fracture prey items. For your convex teeth, they're going to require less force. I actually have a helper who has my teeth models, and at this time, she should pass them out so you can see the difference in the radius of curvatures. So there's 5 different teeth, and they range from a -6 radius of curvature, which is going to give you that concave shape, a -10 radius of curvature, which is a little bit less, a flat model for the in-between, then you have your 2 different convex radius of curvatures with a 10 radius of curvature that's kind of closer to the flat, closer to the -10, and then a convex radius of curvature that's 6, which is going to be the most bulbous and round at the top. So for these teeth, we needed something to smash. And first, you're just like, yo, why don't we just go out and get the shells to eat? Like, obviously, that'd be the best idea. It's not. So the problem with live shells in nature and everything is that nothing is the same. You can't have identical things across the whole board. So in order to lower some of that variance that we see, we're going to go ahead and make a uniform shape that's going to be brittle, readily available to me, an REU student with a small budget, we should talk to NSF. But we needed something readily available, brittle, and kind of the same across all spectrums. For that, we got these guys. So this is just filter media. You can get them from any one of your aquarium fish type stores. And we borrowed the idea from another study that used these to test the crushing ability of pharyngeal teeth. So to crush these little shells with our awesome teeth that I made from aluminum metal, we used a material testing system. So what this machine does is you enter a program into it, and depending on what you put into it, the machine is going to perform that program. For us, again, we're checking crushing ability, so we needed to come down at a constant rate and apply this force to our prey item. So over the course of time, you're going to have this slow-moving crosshead coming down, just applying like a rate of force until this machine goes ahead and pops. So I have a quick video of the crosshead moving down. I think it's started by hand. It's not going to be sideways when I do it, and you will be amazed. I don't even think it's going. Calm down, naysayers. Hold on, I might want to click it well enough. All right, so this was my life right here. Come on, I'm not going to do it. Oh, performance issues. 1 out of 3. One more time. All right, let's check. Does it look like it's moving anywhere? Oh, there it is. Okay, bam. Come on. Oh, I'm gonna cry. But that's actually pretty much what happened in the lab because I'd be sitting there and the crosshead's coming down and I'm like, oh, cool. And then like people who watch my show, oh, is this where it cracked? And then there's this small satisfying crunch where it just breaks into 4 equal pieces. I'm like, woo! And then joke and assess it is, but it's just like, oh, that's it. But yeah, no, it's awesome. I loved it, and I did 800 of these, and every single one of them were amazing each time. So the MTS gives us this graph, which is going to show you the force on the y-axis over the distance that the crosshead moves in millimeters. So right here is going to be what we're looking for. At this point is going to be when the prey item fails and it just, bam, smashed by the teeth, which are doing exactly what we want them to. That is what we didn't want, or what we did want, depending on what kind of teeth we're using or what kind of trend we're trying to see. So the lower the peak, the more effective your teeth is. The higher the peak, the more effective, or the least effective your teeth is. All right, all over the place right now. All right, so we had all these different models and then had all these different teeth, and again, nothing's perfect in nature, so we needed to find a way to normalize the variance that we would see in the prey model. So we got their volume, and for this graph that's going to be quite scary, prepare yourselves, we have the force per volume, the force that's normalized per volume against all of that. So bear with me here. When we're looking at this, what you want to do is go ahead and, again, force normalized per volume, and on the x-axis we're going to have tooth arrangements separated by colors with their arrangements underneath in case the colors running up, just to make sure everyone understands. And then going along, we have the concave convex series that you can see in the model. So looking at this, just right off the bat, I see, cool. The linear does not seem to be doing much. It's just flat across all bases. I don't really see a trend. Let's move on to the next one. Now this one was really cool because for these tests, I saw that the concave was actually outperforming what I thought the convex was. Because you see this upward, 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 and I'm like, cool. Concave is working better in arrangement than convex. And then right where that 6 should have been above that 10 millimeter radius of curvature, there's a drop. And why? So you see the same thing, kind of this upwards, 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 then dropping. So to kind of pull away from this big sphere graph, I'm going to look at each of the teeth arrangements individually. So again, the linear one showing exactly what I thought I'd seen, where there's not much change in between any of the tooth morphologies across the entire series. So you're going to see that they all pretty much require about the same force to cause failure in their prey items. In the staggered series, the only significant one that's different from the rest of them is going to be that one right there. So pretty much, statistically speaking, the concave -6, the concave -10, even the flat one, which are just supposed to be there so that you can see the difference between concave and convex, and the 6 millimeter radius convex are all performing on the same levels. Same for the quad series, and where it's supposed to be same for the modified quad series, it's not. So this looks a little bit more similar to the linear arrangement, where you have kind of a flat, linear type thing going on here, and then the 10 has an increase which is different from the flat significantly by statistics and whatnot, statistically significant. Right there, and then right where this one's supposed to drop down and be just like these other three, it doesn't. So the question was why? I could have just stopped there and been like, you know what? Tooth plates are different. I proved that. You know, science done. Bam, boom. But we wanted to go ahead and look more at it. So if you again look at this bigger graph, you see clearly that you have these two convex 10s that are performing way worse than the other ones, which for all intents and purposes might as well be on the same line here. Why is that? So looking at the convex tooth, the 10 that was performing on all points worse than the rest of them, we see this kind of upward trend, and it's kind of like a parabolic shape where it goes from the linear, which is normalized across all points, to the staggered, to the 10, back to, to the quad, back to the modified quad. Statistically, these two were the same, and these two were the same. And there wasn't like a definitive answer that came straight from that. But it was just crazy to me to see that if you go from arrangement, this same tooth, like identical morphology as all the rest of them, whereas if you think about it, like you got one tooth, you know, should work as well as the other tooth, that's exactly the same. But it's not. So from this, we got by themselves, the linear tooth arrangement was statistically different from the quad arrangement, regardless of tooth morphology, which doesn't really do much for our study because no matter how much you want them to, you can't have a plate without teeth because that's, you know, they don't work like that. You can't have this arrangement with no teeth on it because it can't exist. So for the concave and the flat, there was no difference as well, which was, again, mind-boggling because the flat was not even supposed to be like really a part of this, supposed to be like kind of out, but we keep seeing this flat performing just as well as the concave teeth.